The shock absorber is one of the fundamental elements of the vehicle's suspension system. Its function is to stop spring oscillations, providing control, grip, stability and comfort to the occupants of the vehicle. Shock absorbers today are hydraulic devices, i.e., they work on the basis of oil flowing through valves, the damping rate of which is sensitive to the speed of the piston. Therefore, the faster it moves, the more resistant the shock absorber is to movement, thus becoming more rigid. The most common type of shock absorber currently used in motor vehicles is the hydraulic telescopic type. Although there are other variants on the market, most units are built with 1 or 2 cylindrical steel tubes with a rod moving up and down inside, which is attached to the vehicle. The system includes calibrated valves that allow compression and rebound forces to be adjusted by controlling the oil flow through them in different driving situations. Twin-tube shock absorbers, as the name suggests, have a body made of 2 concentric tubes. These tubes create the working chamber and the reserve chamber. For the shock absorber to perform its function properly, the working chamber must be full of oil at all times. Otherwise, the valves will be operating in air, causing them to malfunction. The reserve chamber will always be partially full of oil because its function is to ensure that the working chamber fills with oil, regardless of how compressed the shock absorber is. Both tubes are separated, and a compression valve is located at the base of the working chamber tube. The standard design of any twin-tube shock absorber also includes a piston rod with a piston valve moving up and down inside an oil-filled cylinder known as the working chamber. This rebound valve comprises 3 types of basic elements that control oil flow. Flexible discs with the bleed perforations required to control force at low piston speed, 0.12 meters per second. The set of flexible discs necessary to control force at medium speed, 0.42 meters per second. And a perforated central cylinder or interface which manages the force when the rod moves at high speed, 0.76 meters per second. In twin-tube shock absorbers, we also find a compression valve at the base of the working chamber tube. The configuration of this valve is similar to the piston valve, but inverted. It is also smaller in size because its design takes into account the damping force provided by the coil springs during compression and other elastic elements of the suspension system. When the shock absorber compresses due to uneven ground, the rod enters the working chamber, increasing the pressure of the oil contained internally. During this so-called compression phase, the compression valve controls the resistance of the damper movement, while oil flows almost freely from the bottom of the working chamber to the top through the piston valve. Increased oil pressure in the working chamber causes the compression valve to progressively open, and the excess oil to flow into the reserve tube in a controlled manner. During the rebound movement, the piston rod leaves the working chamber in a controlled manner due to the effect of the rebound valve. This movement creates a vacuum, which causes oil suction from the reserve chamber, which is equivalent to the volume of the piston rod having left the working chamber during the rebound movement. Thanks to this effect, the working chamber is constantly full of oil. In twin-tube shock absorbers, when the reserve chamber ambient air is replaced with compressed nitrogen at low pressure, 2.5 to 8 pounds per square centimetre, these are called gas-charged shock absorbers, or more correctly, gas twin tubes. This gas charging process is carried out during the manufacturing process. Liquid nitrogen is added to the storage chamber prior to fitment of the oil seals, located at the top of the shock absorber, to prevent leakage. The key advantage obtained by adding pressurized gas to the twin-tube shock absorber is that it avoids the phenomenon known as hydraulic fluid aeration or foaming, which appears when air bubbles form in the oil due to excessive pressure changes occurring when the oil flows through the piston valve as it moves up and down at high speed. Aeration causes noise and inconsistent shock absorber performance due to the air flowing through the valves. In the case of the gas twin-tube shock absorber, the low-pressure compressed nitrogen gas prevents the formation of air bubbles, which produce the aeration problem and also their negative consequences for vehicle safety. Gas-charged shock absorbers offer other significant advantages over hydraulic oil shock absorbers. The pressurized gas in the reserve chamber pushes the oil into the working chamber, keeping it constantly full. This effect eliminates the need to prime the shock absorber before fitting. Filling with gas creates a reinforcing effect in the shock absorber, which enhances the spring rate of the vehicle. When the shock absorber is compressed, the rising oil from the working chamber enters into the reserve chamber, compressing the gas housed in it. When the shock absorber begins to rebound, the force of the expanding gas helps the shock absorber to rebound more quickly. As a result, the shock absorber responds quicker, helping to keep tyre contact with the ground for longer, increasing the safety of the vehicle due to better tyre grip and more effective steering.